Good morning, welcome to the lecture series of operating systems. In today's class, we try to discuss about the classic problems of synchronization. In the classic problems of synchronization, we try to discuss about the three problems. The first one is the producer-consumer problem. This problem is also be called as the bounded buffer problem. And the second one is the readers-writers problem. And the third one is the dining philosophers problem. So first we try to discuss about the producer-consumer problem. In the producer-consumer problem, first we try to discuss about the producer, consumer, and what is the bounded buffer problem. So the name producer, the name itself indicates that any process which produces the items, that process is called as a producer. So what are the examples of the producer process? For example, we are assuming that a process is simply generate the data and that data is given to the another process. So automatically which process generates the data, that process is called as a producer. One of the examples is, for example, in one of the process, it simply collects the data from the end user and that data is given to the another process. So automatically which process it collects the data, that process is considered as the producer. Now we try to discuss about the consumer. The name itself indicates that it simply consumes the items which one is produced by the producer process. That is nothing but whatever the data is collected by the producer process, the consumer takes that data and perform the operation and provide the results to the end user. Those process is called as the consumer. Now we try to discuss about the bounded buffer. Actually in the producer consumer problem, whatever the producer produced, those items are placed into the buffer. And what is a buffer? Buffer is nothing but the temporary storage area. So those items are placed into the buffer and whatever the items are available in the buffer, the consumer simply consumes those items. For example, the temporary storage space, if it is having the infinite space, then it is considered as the unbounded buffer. If there is a fixed space, then it is considered as a bounded buffer. And whenever a buffer is said to be bound, that itself indicates that there is a maximum limit. Example, it is possible to store 100 items or the 1000 items or 10,000 items. There exists a maximum limit to store the items on the buffer, then that buffer is called as a bounded buffer. So already we understand the producer is nothing but the process, it simply produces the items and whatever the items are produced, those are placed into the buffer. And similarly the consumer, it simply takes the items from the buffer and simply perform the consumption operation. And the bounded buffer is nothing but whatever the space is available to store the items produced by the producer, there exists a maximum limit, then that one is called as the bounded buffer. Actually the producer consumer problem is also be called as a bounded buffer. Why it is called as a bounded buffer? We are assuming that the temporary space is available to store the items produced by the producer is having the maximum limit. For that reason, it is called as a bounded buffer problem. Now we try to discuss about what is the need of this synchronization between the producer and the consumer processes if they are using the bounded buffer. For example, we are assuming that the producer produces the items and those items are placed into the buffer, and we are assuming that the maximum size of the buffer is 100. So the producer is allowed to place the first item in the buffer, second item in the buffer, and so on. 100th item is also be placed onto the buffer, and the consumer not takes any item. So automatically the entire buffer is full, because we are assuming that the buffer is a finite space. It is possible to store only the 100 items, and the producer is produced 100 items. These items are placed into the buffer, and the producer produced one more item, but there is no free space is not available. So producer need to wait until the consumer takes the item. So when the producer need to perform the action of the consumer, once the buffer is full and the producer produced an item, that item is not possible to place in the buffer because the buffer is already full. At that time, the producer needed to wait until the consumer consumes the item, then only the free space is generated. the producer process is allowed to place the items into the buffer. So that is the need of the synchronization of the producer process. Similarly, we try to discuss about the consumer process. What is the need of the consumer process synchronization is, generally the task of the consumer is, it simply takes the items from the buffer and perform the consumption, that is nothing but the processing on the item and provide the result to the end user. After completion, again it takes the item from the buffer and so on. For example, the producer produced 100 items and the consumer is also take the first item, second item and so on, he takes the 100th item. So what are the items are placed on the producer in the buffer, the consumer takes all the items. After completion of the 100th item, the consumer wants to take one more item. If there is no item is available on the buffer, so automatically the consumer need to wait until the producer place the item into the buffer. So what is the need of the synchronization of the consumer process? If there is no item in the buffer and the consumer want to consume, that is nothing but he want to take one item from the buffer, at that time the consumer need to wait until the producer place the items into the buffer. So there is a need of the synchronization between the producer and consumer processes. And here we are assuming that bounded buffer is nothing but there exists a maximum limit on the buffer. It may be assumption, it may be the 100. We are able to, the producer is able to store at maximum 100 items. If already 100 items are available and the producer want to place one more item, he need to wait until the consumer consumes the process. So I assume that you understand what is a producer and what is a consumer process, and similarly what is the bounded buffer, you are able to understand. Now we try to discuss about the solution to the producer consumer problem using the semaphores. Now we are discussing about the solution to the producer consumer process using the semaphores. So this is the structure of the producer process. Here what is the task of the producer process? Producer generates the item. Once the item is generated, he need to place the item into the buffer, and before place the item, the producer task verifies the free space is available or not. If the free space is available, directly the producer is allowed to place the item into the buffer. If the free space is not available, the producer process need to wait until the free space is generated, then only he allowed to place the item, and next he produces one more item. So the producer task is, he produces, the space is available, place the item into the buffer and produce one more item. This process is repeated. If the free space is not available, the producer process needed to wait until the free space is generated. So in this structure, the following data structures we are using. And what are the data structures we are using? We are assuming that n is representing the buffer size, that is nothing but how many number of objects are possible to store in the buffer. So n is representing the buffer size. And next one is, we need to use the semaphore. One is the full is a semaphore, and the full semaphore is used to specify that if the buffer is full or not. And similarly the empty is another semaphore, it is our initial value is n, and next one is mutex is another semaphore, its initial value is 1. So here in this algorithm we are using the three semaphores, but these three semaphores in the two different categories. Already in the previous class we discussed about the semaphores in two types. One is the binary semaphore and another one is the counting semaphore. And what is the use of the binary semaphore? It is used to achieve the synchronization. That is nothing but whenever there is a need of the mutual exclusion, that is before modifying the shared data, we need to apply the weight of the binary semaphore, and after completion of the operation we are giving the signal of the binary semaphore. That is the concept is used. So the binary semaphores are used to achieve the mutual exclusion condition. And next one is, there is another type of semaphore is the counting semaphore. What is the use of the counting semaphore? These semaphores are used to count how many resources are available. That is counting purposes, we are using the counting semaphore. In our example, we are using the mutex is a binary semaphore and its initial value is 1. Please note down, the mutex is a binary semaphore and its initial value is 1. Next one is the empty is a counting semaphore. So what is the empty? The name itself indicates that what is the free space is available to store how many items. Initially the entire buffer is free and we are assuming that buffer size is n. For that reason, the initial value of empty is n, and whenever we place on one item, the empty value is decreased by 1. So, every time we place one item into the buffer, the empty value is decreased by 1. So, for that reason, empty is a counting semaphore. Initially, its value is equal to n, because initially all the elements is free. For that reason, there are n number of objects we are able to store. So, the free space empty size is n. And next one is full. Initially, how many objects are existing on the buffer? 0 objects. For that reason, full is representing the counting semaphore. Initially, its value is 0. Whenever the producer placed one item into the buffer, the full value is increased by 1. So, every time the producer placed the item, the full value is increased by 1 and the empty value is decreased by 1. So, the full and empty are the counting semaphores, and mutex is a binary semaphore. It is used to achieve the mutual exclusion condition. What is the need of the mutual exclusion condition? Whenever they are modifying the shared data at any instant of time, only one process need to be allowed to perform the modification to avoid the data inconsistency problems. So, here we try to discuss about the producer consumer process, and this is the structure, and already we know that initially it is the do and it is the while true. What is the meaning of the, if you write a set of statements, those are placed within the do while true, that is while. Here this condition is, it is automatic, every time it is true, that itself indicates that every time the producer produces the item is placed into the buffer. Once the item is placed into the buffer, again he is allowed to produce one more item. So, his task is produce the item, place the item into the buffer, again produce the item. So, it is an infinite process. So, the task of the producer is produce the item, place the item into the buffer, again produce. For that reason, we write the statements within the do while true. And next one is, in this one, what is the first task of the producer? Produce an item. I are assuming that that item is the next produced. So, the producer produced an item, and what is the item name? Next produced is the item name. And whenever the producer want to place the item into the buffer, what is his requirement? He need to verify that the free space is available or not. Where the free space data is available, initially empty is a counting semaphore, its value is equal to n. So, initially there are n number of free spaces are available. Whenever the producer want to place an item, he simply call the wait empty. So, wait is one of the function. It simply takes the empty as a counting semaphore. If the counting semaphore empty value is greater than 0, its value is decreased by 1. If its value is equal to 0, it need to wait, the empty must be greater than 0. For that reason, we are simply using the function wait empty. When the control comes out of the wait function, if there is a free space is available, it simply comes out of the wait function. That is, empty value is greater than 0, it is simply decreased by 1 and comes out of the wait function. If the empty value is equal to 0, the process never comes out of the wait function. That is, the producer process needed to wait until the free space is available. For that condition is simply achieved using the wait empty. And the next one is, we need to place the item into the buffer. The buffer is the storage space. It can be used by the producer to place the item. Similarly, the consumer is used to take the item from the buffer. So, automatically buffer is a storage area. It is accessed by the producer to place the item. Similarly, the consumer to take the item. So, it is a shared memory. So, automatically whenever we are modifying the shared memory location, we need to achieve the mutual exclusion. For that reason, here we are calling the wait mutex. What is the mutex? It is a binary semaphore and its initial value is 1. If there is no process, call the wait function. This is the producer first time, it called the wait mutex. The mutex is set to 0 and comes out of the wait function. So, why we are using the wait function? To achieve the mutual exclusion condition. That is, if the producer want to modify the buffer, consumer is not allowed. Or already consumer starts the operation, he is not allowed. To achieve that one, we are using the wait mutex. And once the control comes out of the wait mutex, the producer placed the item into the buffer. Which item? Already we are assuming the produced item is named as the next produced. The next produced is placed into the buffer. Once the item is placed into the buffer, what is the next operation? The number of elements in the buffer needed to be increased. and so already the buffer is modification is completed. For that reason, they simply give the signal mutex. What is the meaning of the signal mutex? Already mutex value is 0 set by the weight function. Now its value is set to 1 and comes out of the signal function. So here we are modifying the buffer to achieve the mutual exclusion condition. Before modification we are applying the weight mutex. After completion of the modification we give the signal mutex. And the next one is, once the modification is completed, item is already placed into the buffer, then we give the signal full. Already we know that full is a counting semaphore. Initially its value is 0. Every time the producer placed one item, its value is increased by 1. For that reason, how the counting semaphore value is increased by 1? Based on the signal function, the counting semaphore value is increased by 1. So automatically these are the steps need to be followed by the producer process. In the producer process, the first task is the producer need to produce an item. We are assuming that the produced item name is the next produced. Once the item is produced, he need to place the item into the buffer. When the producer is allowed to place the item into the buffer, if there is a free space is available. For the verification purpose, we are using the weight empty. Already we know that empty is a counting semaphore. Its initial value is the number of free slots are available. And every time the producer places the item, the empty value is decreased by 1. Once the empty is equal to 0 indicates that there is no free space is available. If there is no free space is available, he need to wait. The producer process need to wait. For that purpose, it simply called the wait empty. And when the control comes out of the wait function, if the empty value is greater than 0, there is a free space is available, its value is decreased by 1 and comes out of the wait function. If its value is equal to 0, there is no free space is available, the control never comes out of the wait empty until the free space is generated. It is the producer process is stopped here if there is no free space is available. If the free space is available, empty is decreased by 1 and comes out of the wait empty function. Next we are modifying the buffer, placing the item into the buffer. For that reason, buffer is a shared memory area. To achieve the mutual exclusion condition, we are using the weight mutex. Mutex is a binary semaphore, its initial value is 1. If no process is called the wait function, this is the first process is modifying the shared data, the mutex is set to 0, comes out of the wait function, and the whatever the item is existing and the next produced, that item is placed into the buffer, and once the item is placed into the buffer, the other process is allowed to modify the buffer because modification is already completed. For that reason, it gives the signal mutex, and once it is completed, one item is already placed. For that reason, we are giving the signal full. Full is a counting semaphore, its value initially 0. Every time we place the one item, the full value is increased by 1. For increasing purpose, we are using the signal full, and this entire process is repeated infinitely. For that reason, these statements are placed in the do while loop. I hope you understand what is the producer process code is required. Now we try to discuss about what is the code is required for the consumer process. Now we try to discuss about the structure of the consumer process. Already we know that what is the role of the consumer process. The consumer process first need to verify the free space is available or not. Now we try to discuss the consumer process. This is the structure of the consumer process. And first we try to discuss what is the role of the consumer process. The consumer simply takes the items available in the buffer and perform the processing and provide the result to the end user. Next it takes the one more item from the buffer and so on. It is repeatedly takes the items from the buffer and perform the process. If there is no item available in the buffer, the consumer process need to wait until the producer places the item into the buffer. So automatically, what is the role of the consumer process? It is also be infinite loop, and it repeatedly takes the item, perform the processing, and next takes the next item, and so on. If there is no item is available, the consumer process need to wait until the producer places the item into the buffer. For that reason, in the consumer process is also be placed within the do while loop, and while loop condition is also be true. That is, every time whenever we are verifying the condition must be true only. So it is an iterative process. And next one is here in this consumer process, the first consumer, what is the role, first requirement? He must verify item is available or not. Already we know that what are the data structures we are using in the producer process. The same data structures the consumer process is also using. The full is a counting semaphore. Initially its value is 0. Every time the producer placed an item into the buffer, using the signal function, the full value is increased by 1. So at that particular time, full value is equal to 10 indicates that there are the 10 items are available in the buffer. Or the full value is equal to 5 indicates that there are the 5 items are available in the buffer. Or the full value is equal to 0 indicates that there is no item in the buffer. So full is representing at that time how many number of objects are available in the buffer. So the full is one of the counting semaphore. Initially its value is 0. Every time the producer placed an item into the buffer, using the signal of full, the full value is increased by 1. And similarly, what is another one? Empty. Initially it is also be a counting semaphore. Initially its value is n. There are the n number of what is the maximum buffer size. Every time the producer placed an item, using the weight empty, its value is decreased by 1. So automatically empty is equal to 10 indicate that at that time there is a free space to store the 10 items. So already I assume that you understand empty is a counting semaphore. It clearly specifies what is the free space is available in the buffer, and another one is the full is also be a counting semaphore. It clearly specifies how many objects are available in the buffer. And next one is, so these are the two, and next one is mutex is a mutual exclusion purpose we are using. It is a binary semaphore. Initially its value is 1, and whenever we are modifying the shared data items, we are using the wait mutex. After completion of the modification, we are giving the signal mutex. The other process is allowed to perform the modification on the shared data items. So here in the consumer process, the first task is the consumer need to verify the item is available in the buffer or not. For that reason, he simply calls the wait full. Full is a counting semaphore. Its value is representing how many objects are available in the buffer. What is the role of the wait function? If a full value is greater than 0, it is simply decreased by 1 and comes out of the wait function. If full value is equal to 0, this process need to wait in the wait function only until full is greater than 0, then only it is decreased by 1 and comes out of the wait function. So it is used to verify the items are available in the buffer or not. If the items are available in the buffer, full value is decreased by 1 and the consumer is allowed to take the item. If the full value is equal to 0 indicates that there is no item is available, so the consumer process needed to wait until the producer process placed the item into the buffer. So that is the need of the wait full. Now the consumer is allowed, so when the control comes out, already the full is greater than 0, using the wait function its value is decreased by 1, that is items are available, the full is decreased by 1 and comes out of the wait function. That itself indicates that the consumer need to allow to take the item from the buffer. Buffer is a shared memory. So whenever the consumer is allowed to take the item from the buffer, others are not allowed. That is, the producer is not allowed to place, because both are allowed to perform the modification in the buffer, shared memory. There may be the possibility of the data inconsistency. To overcome that one, to achieve the mutual exclusion condition, we are using the wait mutex. Similarly, in the previous algorithm also in the producer process, before place the item, they are using the wait mutex. After placing the item, they give the signal mutex. Similarly, in the consumer process also, before allowing the consumer to take the item from the buffer, we are giving the wait mutex. Next, once the wait mutex is completed, if the mutex is 1, it is set to 0, comes out of the wait function. Then the consumer process remove an item from the buffer, and we are assuming that that item name is the next consumed. So the consumer process takes one item from the buffer, and we are assuming that item name is the next consumed, and once item is taken from the buffer, so modification is over, then it gives the signal mutex. So I hope you understand why we use the wait mutex and signal mutex is because the producer process modifying the buffer, and the consumer process is also modifying the buffer. So, buffer is a shared memory location. At any instant of time, only one process is allowed. Either the producer is allowed to place the item or the consumer is allowed to take the item. Only one is allowed. For that reason, to achieve the mutual exclusion condition, we are using the wait mutex and signal mutex. So, the consumer already take one item from the buffer. Once the item is taken, automatically the free space is generated. For that reason, here we are using the signal empty. Why we give the signal empty? Empty value is simply increased by 1, because already the consumer process takes one item from the buffer. For that reason, they simply give the signal empty. So, automatically empty value is increased by 1. And once that is completed, the consumer process consumes the item, that is nothing but it performs the processing of the next consumed, and once the processing is completed, again the consumer goes to take the next item from the buffer. In that way, the consumer process is allowed to perform. So, here in this one producer consumer problem, to achieve the process synchronization, what are the data structures we are using? We are using empty is a counting semaphore. Initially its value is equal to the buffer size, that is equal to n, and full is a counting semaphore, its initial value is 0. And next one is the mutex is a binary semaphore. At any instant of time, either the producer or the consumer, only one is allowed. To achieve the mutual exclusion condition, we are using the mutex is a binary semaphore, its initial value is 1. Before modification on the buffer, they give the wait mutex. After completion, they give the signal mutex. So, automatically we try to discuss, go through it. What is the task of the producer process is, first producer generate the item. We are assuming it is the next producer. Once the producer produces the item, he need to verify the free space. For that reason, they call the wait empty. Once the control comes out of the wait function, indicate that there is a free space is available, and empty is decreased by 1 and comes out of the wait function. And now producer need to place the item into the buffer. For that reason, they give the wait mutex. Once the control comes, indicate that consumer is not performing the modification on the buffer, then only the mutex is 1, he is allowed to set it to mutex is set to 0 and comes out of the wait function. Producer places the item into the buffer. Once it is completed, he gives the signal mutex, that is, once the operation is completed, if the consumer is waiting, he is allowed to take the item from the buffer. And once the item is placed, then automatically the full need to be increased, because the full is representing how many items are available on the buffer. For that reason, he gives the signal full. So, this is the code is used for the producer process. Similarly, in the consumer process, the consumer first need to wait for the free space. For that reason, they call the wait. So, consumer. Similarly, in the consumer process, the consumer first waiting for the object. For that reason, you use the wait full. Whenever the full is greater than 0, indicate that the items are available. It is decreased by 1, comes out of the wait function. And before performing the modification on the buffer, that is before take the item from the buffer, he gives the wait mutex, and after taking the buffer, he gives the signal mutex, and after completion of that one, he gives the signal empty. The reason is the producer is allowed to place one more item, because already the consumer takes the item. For that reason, empty value is increased by 1 using the signal empty, and the consumer consumes the item. After consumption, that is after processing the item, the consumer is allowed to take the next item. So, it is an iterative process. I hope you understand what is the producer consumer problem. It is also be called as a bounded buffer problem, and how to achieve the solution for the producer consumer problem. In the next class, we will discuss about the readers writers problem. Thank you. Good morning. Welcome to the lecture series of operating system. In the previous class, we started the classic problems of synchronization, and we are already discussed about the producer consumer problem. In today's class, we try to discuss about the readers writers problem. In the readers writers problem, first we need to understand what is a reader process and what is a writer process, and what is the problem in the readers writers problem. First, we try to understand what is a reader process. The name itself indicates that any process which perform only read the items from the memory, then that process is considered as a reader process. For example, a process only performs the read operation, then any number of readers are allowed to perform the read operation, because they are not performing the write operation, that is they are not allowed to modify, only read the data. So, any number of processes are allowed to perform the read operation, there is no problem is existing. So, I hope you understand what is a reader process. That reader process, the name itself indicates that it only performs the read operation on the shared data. It is not performing any modification on the data, then that data is considered as a reader process. Now, we try to understand what is the writer process. The name itself indicates that it performs the write operation, that is, it performs the modification on the shared memory location, or whatever the shared data is existing, they perform the modification. Then that process is called as a writer process. So, I hope you understand, a process performs only the read operation. Without modifying the data, they perform only the read, then that process is called as a reader process. And a process perform the modification on the shared data, then that process is considered as a writer process. Now, we try to understand the writer's problem. So, what is the writer's problem? So, the problem clearly says that any number of readers are allowed to perform the read operation. If any number of readers are allowed, there is no problem. They simply read the data and they perform their own operation. It is not gives any data inconsistency. But one writer is performing the write operation, no other reader is not allowed, because the data is already in the modification process. In that middle of the process, if the reader is allowed, he is unable to get the correct information. So, automatically, if a writer process performing the write operation, no reader is not allowed. Similarly, if more than one writer is also be allowed, we get the data inconsistency problem. Already we discussed in the first class, more than one process is allowed to modify the shared data, we get the data inconsistency. For that reason, at any instant of time, only one writer is allowed, but any number of readers are allowed to perform the read operation. And one more important one is, whenever the writer, we need to allow the writer process to perform the write operation, no writer is already performing the write operation. In addition to that one, no reader is also performing the read operation, because one reader is already performing the read operation. In the middle, we are allowing the writer to perform the write operation. In the middle itself, the data is modified, the reader process is consumed. In the beginning of the reader process, it has get the one data, in the middle it is already modified. So, automatically there is a problem may be arise. For that reason, once the reader is already performing the read operation, writers are not allowed. So, I hope you understand what is the writers problem. Now, we try to discuss how to provide the solutions to the writers problem. Now, we try to discuss about the writer process structure. Already we know that the writer process is performing the write operation on the shared data. Whenever we are allowing a writer process, no writer is already performing the write operation and no writer is performing the read operation. At that time only the writer needed to be allowed. And once the writer is allowed, from that time onwards, no other writer and no other readers are not allowed to perform their operation until the current writer completes its operation. Once it is completed, now we are allowing either the readers or the other writer may be allowed to perform the operation. To achieve these constraints or to achieve these requirements, we are using the following data structures. And what are the data structures we are used in the writers problem is, we are using the RW mutex. It is one of the binary semaphore. RW is nothing but the reader writer. That is nothing but before allowing any writer or the reader, we are using the RW mutex is a binary semaphore. We call the weight of RW mutex. So, RW mutex is a binary semaphore and its initial value is 1. I hope you understand what is RW mutex is a binary semaphore. Its initial value is 1. It is used to achieve the process mutual exclusion condition, that is at any instant of time only one writer to be allowed, or already one writer is performing the write operation, we stop the other readers. For that purpose we are using the RW mutex binary semaphore. And another one is read count is one of the variable. Initially its value is 0, and whenever readers are allowing, every time a new reader is allowed, the read count is simply increased by 1. So, the read count clearly specifies that at that particular time how many readers are performing the read operation. Initially the read count value is also be 0. And one more is the mutex is a binary semaphore. To achieve the synchronization purpose, we are using the mutex semaphore. Now, we try to understand the writer process syntax. So here whenever we need to allow the writers to perform the write operation, what is the requirement? There is no other writer is already performing the write operation, or there is no reader is performing the read operation. To achieve that one, we are using the wait RW mutex. Either the reader is already performing the read operation, at that time RW mutex is set to 0 based on the wait function. If there is no reader is performing the read operation and no writer is performing the write operation, at that time only RW mutex value is 1. That itself indicates that there is no writer is performing the operation and no readers are performing the read operation. We are allowing the writer to perform the write operation. For that reason, wait RW mutex. I hope you understand what is the need of this one. So automatically based on this one, the first writer is allowed to perform the write operation. So I hope you understand what is the use of the wait RW mutex is. RW mutex is a binary semaphore. Its initial value is 1. If there is no reader and no writer is performing the write operation, at that time only the RW mutex is 1. Then using the wait function, RW mutex is set to 0 and it comes out of the wait function. So automatically the first writer is allowed to perform the write operation, and once the writer is performing the write operation, he completed its operation, then he called the signal RW mutex. That is, he completed the write operation, then the RW mutex is set to 1 and he comes out of the write operation. So automatically the structure of the writer process is a simple one. Before perform the write operation, is simply called the wait RW mutex. RW mutex is a binary semaphore. If its value is 1, it is set to 0 and comes out of the wait function, and the writer performing the write operation, and once the write operation is completed, he simply gives the signal RW mutex. Now we try to understand the structure of the reader process. In that reader process, whenever we need to perform the read operation, we need to increase the read count, and read count is one of the global variable. Initially its value is 0. Whenever the reader process want to perform the read operation, read count is increased by 1. We know that there are the n number of reader processes, they are able to perform the read operation. So automatically any process want to perform the read operation, read count is increased by 1. So the read count is a shared variable, and whenever the process is allowed, no other process is not performing the increasing the read count value. For that reason, before increasing the read count, we are using the wait mutex. Already we know that mutex is a binary semaphore. Its initial value is 1. If any first reader process perform the read operation, it simply called the wait mutex. Mutex is set to 0 and that reader process is allowed to increase the read count by 1. Once it is increased the read count by 1, now we are verifying if read count is 1, that itself indicates that this is the first reader process want to perform the read operation. If that is the first reader process perform the read operation, then writers are not allowed. For that reason, to stop the writers to perform the not allowing to perform the write operation, they are using the wait RW mutex. When we are calling the wait RW mutex, once we call the RW mutex is a binary semaphore. Initially its value is 1. Either the writer process wants to perform the operation, they call the wait RW mutex. For example, we are assuming that already writer is performing the operation, write operation. At that time RW mutex value is 0. And this is the first reader to perform the read operation. Read count is increased by 1. Then automatically read count is 1. Now we call the wait function. This reader is not allowed to perform the read operation because already writer is performing the write operation. Once his write operation is completed, then only this reader is allowed. To achieve that one, we are writing the condition if read count is equal to 1, that is this reader process is the first reader process. Now we are verifying is there any writer is performing the write operation. This must be blocked. This must wait until write operation is completed. To achieve that one, we are using the wait RW mutex. I hope you understand why we write the wait RW mutex. Once the control comes out of the wait function, indicates that there is no writer is performing the write operation. Then only the RW mutex is 1. and based on the weight function it is set to 0 and comes out of the weight function. Once it is set to 0, other writer is not allowed. He must stop in the weight RW mutex function only. For that reason we are using the weight RW mutex. Once it is completed, we give the signal mutex. What is the need of the signal mutex? Because we are modifying the read count. Once it is complete, modification is completed and we are verifying the condition of this condition is satisfied, then we give the signal mutex. Other reader processes are allowed to perform the modification on the read count. So I hope you understand this is the code is used in the entry section of the reader process. What is the code is required? Whenever the reader is allowed to perform the read operation, read count need to be modified, and read count is a shared variable. Any reader process modifying the read count, so automatically at any instant of time only one reader is allowed to perform the modification. To achieve the mutual exclusion condition, we are using the weight mutex and signal mutex. So automatically before modification of the read count, we are using the weight mutex and signal mutex. What is its advantage? At any instant of time only one reader is allowed to modify the increasing the read count value. And once we are increasing the read count value, what is our next requirement? After increasing read count is equal to 1 indicates that this is the first reader process is allowing to perform the read operation. Before allowing, we need to verify that there is no writer is performing the write operation. Once the writer is allowed, RW mutex is set to 0. For that reason, we are calling the weight RW mutex. If RW mutex is 1, there is no writer is performing the write operation, it is set to 0, comes out of the wait function. If it is already 0, that this first reader is need to wait until the writer completes this operation. Once it is completed, in the previous algorithm they give the signal RW mutex. Based on that one, this reader is allowed, set it to 0 and comes out of the wait function. And once the reader is allowed to perform the read operation, no writers are allowed, because once it executes the weight RW mutex is set to 0. If any other writer try to write operation, he is waiting in the wait function only. He is not allowed to perform the write operation. So automatically once it is completed, the reader is performing the read operation. So automatically once the read operation is completed, what is our next goal? We need to decrease the read count, because once the one reader is completed its operation, read count need to be decreased. For that, so we need to modify the read count. It is a shared variable, and before perform the modification we give the weight mutex, and after completion we need to give the signal mutex. I hope you understand. Mutex is a binary semaphore. Before modification we need to call the weight mutex. After completion we need to give the signal mutex. And once we call the weight mutex, only the one reader is only allowed to perform the modification of the read count. Now we are decreasing the read count minus, because one reader is completed its operation, the read count is decreased by 1, and once decreasing the read count, we are verifying that if read count is equal to 0, if the read count is equal to 0, indicate that this is the first, this is only the reader is reading the operation, it is completed. Now we are allowing the writer. For that reason, we give the signal RW mutex. RW mutex is a binary semaphore. At the time of the first reader to perform the read operation, we set the RW mutex is equal to 0. Then any number of readers are allowed to perform the read operation. All the readers completed their read operation. Then only the read count is equal to 0. At that time, we give the signal RW mutex, that itself indicates that other writers are allowed to perform the write operation. Once it is completed, it gives the signal mutex. So automatically after completion of the read operation, what is the operations we need to perform? We need to decrease the read count by 1. But read count is modified by the n number of readers. At any instant of time, only one reader to perform the modification. To achieve the mutual exclusion, we are using the weight mutex and signal mutex. Between these, we need to perform the modification. What is the modification we are performing? We are decreasing the read count by 1. Read count is decreased by 1. If read count is equal to 0, that indicates that no other readers are performing the read operation. If any writers are waiting, those must be allowed. To achieve that one, we are giving the signal of the RW mutex. So automatically other writers are allowed to perform the write operation. So this is the code for the readers writers problem. Now we try to discuss with one example. We are assuming that there are the two writers W1, W2, and 3 readers R1, R2, R3. They perform the operations. For example, initially first writer W1 want to perform the write operation on the shared data. And what is the algorithm we discussed for the writer process? They simply use the function is the wait RW mutex. Already we know that what are the semaphores we are using in this algorithm. We are using the algorithm is, now we discuss with an example for the readers writers problem. Let us, we are assuming that, so there are the 3 writers are, now we are assuming that 2 writers are existing. One is W1 and another one is W2, and 3 readers R1, R2 and R3. So we are assuming that 2 writers W1 and W2 and 3 readers R1, R2 and R3. Already we know that in the readers writers problem we are using the semaphores. Mutex is one of the binary semaphore, and another one is the read count is an integer variable, and another one is the RW mutex is also be the another binary semaphore. So we are using the mutex is a binary semaphore, its value is 1, initially read count is 0, and the RW mutex is also be the binary semaphore, its value is equal to 1. Now we are assuming that W1 process wish to perform the write operation, and there is no reader is performing the read operation. For that reason read count is 0, and first W1 process want to perform the write operation. Already we discussed about the writer process code. What is the writer process code? They are using the wait RW mutex. After if the process comes out of the wait function, when the process comes out of the wait function, if RW mutex is 1, it is set to 0 and comes out of the wait function, then the writer is allowed to perform the write operation. There is no reader and writer is performing the write operation. For that reason RW mutex value is equal to 1. So automatically if the W1 process simply calls the wait RW mutex, its value is set to 0 and comes out of the wait function, that is W1 process performing the write operation. I hope you understand. W1 process is allowed to perform the write operation. If you want to see the code, you just go through it. The W1 process simply calls the wait RW mutex. Its value is already 1. For that reason it is set to 0 and comes out of the, its value is 1, it is set to 0 and comes out of the wait function. Now W1 process is performing the write operation. Now we are assuming that if the reader process R1 perform the read operation, what is the operations are allowed by the read operation? Already in the code we are already discussed. Whenever the reader want to perform the write operation, they need to increase the read count, but the read count is a shared variable. For that reason they simply call the wait mutex. If you want to verify the code, we go through the code. What is the first operation is performed by the writer process is, first it simply called the wait mutex. Already mutex value is 1. For that reason it is set to 0 and the read count is increased by 1. So automatically read count is initially 0, it is set to 1. If read count is equal to 1, wait RW mutex. Already W1 is performing the write operation. For that reason RW mutex value is 0. For that reason this reader process is not comes out of the wait function. If you want to verify this one, already we are discussed in this one. Already W1 is performing the write operation. At that time RW mutex is set to 0 and first reader want to perform the read operation, mutex is set to 0 and read count is increased by 1 and it calls the wait RW mutex, but its value is already 0. The reader R1 is not comes out of the wait function. It is waiting for the completion of the writer process. So automatically R1 is not allowed. For example, R2 want to perform the read operation, again it calls the wait mutex, but already mutex is 0 because R1 is modifying the read count. Once it is completed only it gives the signal mutex. So R2 is also be not allowed in the wait mutex itself only. For example, so any other readers are not allowed. So for example, W1 is completed the write operation. What is the next statement after completion of the write operation in the reader process is simply gives the signal, it gives the signal mutex signal RW mutex function. So automatically it gives the signal RW mutex, it is simply set it to 1 and writer is completed the write operation. Once the writer completed the write operation, already reader process is waiting for the wait RW count function. For that reason in the here in the previously R1 process is waiting. R1 process is waiting for the RW process is waiting for the wait RW mutex. So automatically it is already set by 1 by the wait W1 process. For that reason it is set to 0 and comes out of the wait function, and the reader is gives the signal mutex, it is value is increased by 1 and R1 is performing the read operation. Once R1 is performing the read operation, R2 is already waiting for the mutex of wait of mutex. Already it is given, R1 is given the signal for the mutex. For that reason R2 is also be allowed to perform the increasing the read count by 1, that is its value is equal to 2 and our read count is not is equal to 1 condition is false. Without calling the wait RW mutex, it gives the signal mutex well, that is it is again gives the 1 and R2 is also be allowed. So automatically R1 and R2 both are allowed to perform the read operation. If R1 and R2 perform the read operation, if W2 want to perform the write operation, they simply give the wait RW mutex. Already RW mutex value is 0. For that reason automatically W2 process is not allowed to enter into the critical section. When its value is assigned to 0, the first reader, that is the read count is equal to 1 condition is true, at that time it gives the wait RW mutex and it is set to 0 and comes out of the wait function. Then automatically once the R1 and R2 performing the read operations, no writer is allowed. Once these are completed the read operation, so automatically every time read count is decreased by 1, 2 is modified by 1 and the second one is also be completed, it is set to 0. At that time only it gives the signal RW mutex, then it is set to 1, other writer is allowed to perform the write operation. I hope you understand that what is the algorithm we proposed for the reader as well as the writer process. It simply satisfies the mutual exclusion condition. Why they are satisfying the mutual exclusion condition? At any instant of time only one reader or the only one writer or the any number of readers are allowed to perform the read operation, and whenever they are modifying the read count value at any instant of time only one reader is allowed to modify using the wait mutex and signal mutex operations. Similarly the progress condition is satisfied and similarly the bounded waiting condition is also be satisfied by these algorithms. So I hope you understand the readers writers problem and what is the reader process and what is the writer process and what is the problem is existing on the readers writers process and what is the algorithm for the readers process is also I hope you are able to understand. In the next class we will discuss about the dining philosophers problem. Thank you. Good morning. In the previous class we discussed about the readers writers problem. Now we discussed about the dining philosophers problem. In the dining philosophers problem, first we try to understand what is a philosopher, that what is the role of the philosopher, and we try to understand the dining philosopher's problem. So the name philosopher itself indicates that the philosopher is only performing the two operations. One is thinking and another one is the eating operation. That is the philosopher is continuously perform the thinking operation, and whenever he is hungry then only his state is changed from thinking to the eating state. And what is the dining philosopher's problem is, here we are assuming that there are the 5 philosophers, they are continuously performing the thinking operation, and there are the 5 chairs are existing for every philosopher, and there is every philosopher is having one plate, and there are the 5 chopsticks are existing, and whenever the philosopher want to perform the eat operation, he uses the left as well as the right chopsticks. If both the chopsticks are available, then only the philosopher perform the eat operation, otherwise he need to wait until the chopsticks are available. So here the problem is, if all the philosophers want to perform the eat operation, there are the total only the 5 chopsticks are available. It is not possible to perform the eat operation by all the 5 philosophers at a time. So here we try to discuss about the solutions to the dining philosophers problem. So here in the solution to the dining philosophers problem, what are the data structures we are using is, we are using the chopstick is one of the array and its size is equal to the number of chopsticks are existing. Already we know that we are assuming that these are the philosophers is P0. So, we are assuming that the philosophers is the P0, P1, P2, P3 and P4, and the chopsticks are also with the 4 chopsticks are available. We are assuming that these chopsticks, where assumption is chopstick 0 and chopstick 1 and chopstick 2 and chopstick 3 and chopstick 4. So, there are the total 5 chopsticks are available. So, we take the chopstick is one of the array of semaphores, and these semaphores is also with the binary semaphores. Initially the chopsticks are available. For that reason, each chopstick of 0, 1, 2, 3, 4, all the values are equal to 1. So, I hope that what are the data structures we are using is chopstick is one array and its size is equal to the number of chopsticks are available, that is nothing but the 5, and these are represented as the chopstick of 0, chopstick of 1 and so on the chopstick of 4. Initially all the chopstick of 0 to 4, its value is equal to 1. Whenever the ith philosopher, for example, the philosophers are numbered as the P0, P1, P2, P3, P4. If you are discussing about the ith philosopher, that is nothing but the Pi. For example, if we take the first philosopher, at that time we take the philosopher number is 1, I is 1, and the second philosopher we are considered about the P2 we considered, then the I is equal to 2. So, ith philosopher indicates that I is representing the philosopher number, it may be the 0, 1, 2, 3, 4. And what is the solution to the dining philosopher's problem is, whenever the philosopher perform the eat operation, initially he is in the thinking state, whenever he is hungry, then only his state is changed to the thinking to the eating if both the chopsticks are available. For that reason, we are using the weight chopstick of I. So, here when first he takes the, he verifies the right side chopstick is available or not. If the chopstick is available, then only it is set to be 0 and comes out of the weight function. For example, we are assuming that P0 philosopher want to perform the eat operation. So, automatically I is representing as the 0, then he simply call the weight chopstick of 0. If this right side chopstick is available, then automatically it is set to 0 and comes out with the weight function, that is he simply picks the right chopstick. And next one is he simply call the weight chopstick of I plus 1 mod 5. Why it is representing I plus 1 mod 5? Every time it is representing the left side chopstick number. For example, P0 point of view is the left chopstick number is 1, P1 point of view chopstick number is 2, P2 point of view left chopstick number is 3, P3 point of view chopstick number is 4, and P4 point of view is chopstick number is 0. So, automatically every time its value is increased by 1 mod 5. The reason is for the fourth philosopher, left chopstick is nothing but the 4 plus 1, 5 mod 5 is representing as the 0. So, using the weight chopstick of I, the philosopher picks the right chopstick if the chopstick is available. If the chopstick is not available, then automatically the chopstick of I is 0, it is in the weight function only. So, when the control comes out as the weight chopstick of I, if ith philosopher right chopstick is available, then it is set to 0, comes out of the weight function. That itself indicates that the philosopher picks up the right chopstick. And what is the use of the weight chopstick of I plus 1 mod 5? If the left chopstick is also be available, it is set to 0 and he picks the left chopstick and comes out of the weight function. That is, if the control comes out of these two weight functions, indicates that the philosopher picks the right chopstick as well as the left chopstick, then the philosopher is allowed to perform the eat operation. That is, he is performing the eating operation. Once the eat operation is completed, he is allowed to release the chopstick to use his neighboring philosophers to perform the eat operation. For that reason, he simply gives the signal chopstick of I, signal chopstick of I plus 1 mod 5. So, automatically he replaces these chopsticks on the table and his state is changed from the eating state to the thinking state, that is the philosopher is continuously performing the thinking operation, and whenever he is hungry, then only his state is changed from thinking state to the hungry state. At that time the philosopher verifies the chopsticks are available. If they are available, he is allowed to perform the eat operation. If they are not available, the philosopher needs to wait until the chopsticks are available. So I hope you understand that what is the dining philosopher's problem is. Here there is a philosopher, his role is performing the thinking operation to provide the solutions to the problems, but whenever he is hungry, so his state is changed from thinking state to the hungry state. Whenever he is hungry, he verifies both the chopsticks are available, because every philosopher is having the two chopsticks, one is left side and another one is the right side chopstick. If the left and right chopsticks both are available, then the philosopher pick up these chopsticks and perform the eat operation, and once the eat operation is completed, he simply release the chopsticks on the table and he went to the thinking state. So the neighbors is allowed to take those chopsticks. So automatically to implement that one, we are using only one data structure, that is nothing but the chopstick. Its size is 5, because the 5 chopsticks are only available. Initially all the chopsticks are available. For that reason all the chopsticks initial value is 1. And whenever the philosopher picks the chopstick, he simply call the wait function. And whenever the philosopher releases the chopsticks, he simply calls the signal function to release the chopsticks. I hope you understand what is the solution to the dining philosopher's problem. So this is a simple solution. Using the semaphores, we are able to implement the solution. Using the semaphores, its size is the 5. Using the semaphore, its size is the 5. Now we try to discuss the limitations of the previous algorithm. So only their limitation is, if all the philosophers become hungry at the same time and each philosopher grabs the left chopstick, so automatically how many chopsticks are available? 5. So automatically philosopher 0 takes the chopstick 0, philosopher 1 takes the chopstick 1, philosopher 2 takes the chopstick 2, and so on. The philosopher 4 takes the chopstick 4. So automatically every philosopher holds one left side chopstick, and they are waiting for the right chopstick. But the philosopher want to perform the eat operation, both the chopsticks must be available. But here every philosopher holds one chopstick and they are waiting for the another chopstick, so they are unable to complete the eat operation. So automatically this is one of the example of the deadlock problem. Every philosopher holds one chopstick and the philosopher is waiting for the another chopstick held by the another philosopher. So everyone is waiting for the completion of the another philosopher eat operation. So all the philosophers are waiting and it is not possible to get the chopstick, because we are assuming that once the philosopher holds the chopstick, he releases after completion of the eat operation. That is, his state is changed from hungry to the thinking state. So once he completes the eat operation, he will releases. So automatically every philosopher holds one chopstick and they are waiting for the another chopstick. So there is a possibility of the deadlock existence. To overcome that one, there are the several possible solutions are available, and some of the possible solutions to avoid the deadlock problem is, the first one is allow at most 4 philosophers to be sitting simultaneously at the table. That is, at any instant of time, one chair is empty. So we are allowing at maximum 4 philosophers. Every philosopher holds one chopstick. Then automatically one more chopstick is available. One of these 4 philosophers is allowed to use the 5th chopstick. He has completed the eat operation. Then he releases the chopstick. So one of the simple solution is, at any instant of time, only 4 philosophers are allowed, or we are adding one more chopstick to the table. That problem is eliminated. That is one solution. It is a simple solution, but it is not acceptable, because we need to effectively utilize all the 5 philosophers are also allowed to sit on the table. So that is the requirement. So the simple solution is, we are allowing at maximum 4 philosophers, or we are adding one more chopstick on the table. The problem will be solved, but that is not the acceptable solution. What is the another solution is? So the another solution is, if we are allowing the philosophers to pick up both the chopsticks are available. If both the chopsticks are available, and then only the philosopher is allowed to take both the chopsticks at a time, then also the problem will be solved. And another solution is, if you are using the even numbered philosophers, every time they take the left chopsticks, and odd number philosophers they allowed to take the right chopsticks. If you are using that formula also, at any instant of time, only it is not possible. So we are assuming that even numbered philosophers, for example P0, we are assuming that already we know that these are the P0 and P1, P2, P3, P4. And even numbered philosophers are allowed to take the left chopstick, and the odd number philosophers are allowed to take the right chopstick first time. So automatically the deadlock problem is also not possible to occur. So automatically, to eliminate the deadlock problem, there are the possible solutions are, one solution is, at any instant of time only 4 philosophers are allowed, then automatically the deadlock problem is not possible to occur. And another possible solution is, we are allowing the philosopher, if both of the chopsticks are available, then only we are allowing, then also the deadlock problem is not possible to exist. And another possible solution is, even numbered philosophers are allowed to take the left chopstick, and odd number philosophers are allowed to take the right chopstick first, then only allowed to take the another one, then also it is not possible to exist the deadlock. So these are the 3 possible solutions for the dining philosophers problem without occurring the deadlock problem. So we will discuss the producer consumer problem, readers writers problem, and dining philosophers problem. I hope you understand the classic problems of synchronization. Thank you. In the next class we will discuss about the monitors concept.